Okay, so I want to talk about the Carnot cycle. So we've talked previously about basic heat engines, heat pumps, and refrigeration cycles. So those are three classifications of like the top set of cycles. All right, they're not specific, they're just three. Those are the three general types of cycles that you will have, either a heat engine, a refrigeration, or a heat pump. Now the Carnot cycle is a idealized model of a cycle. It's completely reversible. This is like a system that's very theoretical. It's not ever going to happen, but we base everything off this as our basis. Okay, and I'm going to talk about that right now. So the Carnot cycle, and then we're going to get into a Carnot heat engine and a Carnot refrigeration and a heat pump. So a Carnot cycle is an ideal cycle, and this is how it works. So up at the top right, let's look at the PV diagram. So it goes from 1 to 2. From 1 to 2 is a reversible isothermal expansion at a constant temperature. Okay, so 1 to 2. That kind of corresponds to this piston right here. So you have a hot source, you have a source that supplies energy in, and it goes from 1 to 2. So the piston moves down. So the volume increases, the pressure decreases. From 2 to 3, it's a reversible adiabatic expansion. All right, so this corresponds to this condition here. It's insulated and it expands again. Then from 3 to 4, it's a reversible isothermal compression. All right, so this is now no longer insulated up here, and there's a sink. Some of the energy goes out, and then it compresses 3 to 4. So we have heat that goes out. And then from 4 to 1 is an adiabatic compression. It's insulated, and it goes from 4 to 1. All right, so this is the ideal heat engine, the ideal Carnot cycle. All right, and it all is reversible, meaning that it's theoretically, when the piston moves up and down, we're assuming no friction, no losses. All right, so again, 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay, so here is the Carnot heat engine. All right, again, a heat engine supplies high temperature, all right, to the cycle, and you get network out. All right, this cycle is the most efficient cycle. All right, so anytime from future on, if you ever have a cycle that you made or whatever, it will never be higher than this, because this is the most idealized, because it's all reversible. So here's the efficiency, all right, and this is the efficiency of the Carnot cycle. This is of any heat engine, and then this is of the Carnot cycle. And just kind of let you know, if the efficiency of a cycle is less than the Carnot cycle, you have an irreversible heat engine. If it's equal to, then it's basically like a Carnot cycle. It's all reversible. You can't have it greater than it, because it's impossible, because this is the most theoretical condition. All right, so a reverse Carnot cycle, or basically a refrigerator heat pump, works in reverse. If you remember what a refrigerator and a heat pump is, they basically draw energy away from a certain section and either cool it or heat it. If they draw it away to cool it, if they supply heat in, they're heating it, heat pump. Okay, so we have coefficient of performance of a heat pump, and then I gave you the efficiencies of the Carnot. All right, and again down here, coefficient of performance is when we deal with refrigerators or heat pumps. Okay, so it's very brief, but just remember, there's three general cycles: heat engine, refrigerator, and a heat pump. And then the Carnot cycle is the most theoretical. Basically everything we model, it's the most theoretical model that we use and compare other models or other cycles to. And again, this is the general idea of a Carnot cycle. And this is a heat engine, supplies reservoir in, supplies work out, and then you have refrigerations where you have Q in, and then QH goes out, which is reverse of a heat engine. Okay.